Hi, everyone. Welcome to our seminar. Today we have Ling Lin. Lin received his BS degree from computational mathematics from Peking University in 2007 and PhD degree in applied and computational mathematics from Princeton University in 2011. His research interests include quantum algorithms for scientific computing, and neural network methods for quantum systems. He's now an associate professor in the Department of Mathematics at UC Berkeley, a faculty scientist at Berkeley Labs mathematics group within the CRD division, and a mathematician with the Camera Center. They also received a number of awards, which I will skip for this session. You're welcome to check out the details from the website. With this, I'd like to hand it over to Lin.
Thank you, and I'm glad to give a talk. And I was the 2011 Alvarez Fellow. I think this is a great program, and so because the audience is general, and I will really talk about something about myself first. I mean, how I came to become interested in quantum information sciences, and then talk about quantum eigenvalue problems. So if you're interested in the details, this is a joint work with two fantastic grad students. The first one, Yutong, who just graduated and has moved to Caltech IQIM fellow. And the other is Yulong Dong, who is currently a grad student in the math department, jointly advised between Brigitte Willi and myself. And these are the references related to the topics discussed today. I want to say something about myself first, which is, I started my PhD in 2007, and I found that there's in the group, they're doing a lot of ab initio or first principle calculations, and they produce this very cool VND movies. Let me show you one of them, and presumably it's even working, but I do need to click the link here. Can you see this? See my screen?
Yes.
Yeah. So these are like ab initio path integral molecular dynamics simulation. Unfortunately, I couldn't find the things I did myself yesterday, so I just give a YouTube link. And these molecules, they move around and they really follow first principle calculations. And you see all these things, and these are like each quantum hydrogen represented by a classical string. And use this, you can derive a lot of nice properties that matches with the experimental result. I was pretty fascinated by this kind of movies. What you do, it's very different from what I did or have seen during my undergrad. So I want to know more. I was very fortunate to be advised by Professor Wenan in the math department and Professor Roberta Ka in chemistry. So I wrote a thesis titled, that's a large title, density functional theory and the nuclear quantum effects. And what it's really about is large-scale DFT calculations for metallic systems, and also on new methods related to path integrals and related calculations. So I was pretty happy about that, although it wasn't very standard path as someone from the applied math department. I spent pretty much a third of my time at the Freak Lab, which is the chemistry department, and in Princeton. So after graduation, I got a few possible offers. In the end, I decided to take the Alvarez Fellow because at that time I feel quite strongly that I want to make the method, which is called the Poe expansion and selective inversion, PEXI, method that started being developed during my PhD together with my fantastic collaborators, Lexing Ying at Stanford, Jianpeng Lu at Duke, and Chao Yang at LBL. And I want to make that method into the electron structure community, not just working with a 5-point stencil. I mean, you prove that this thing works and therefore the problem is done. I really want this method to be used by actual physicists, chemists, material scientists, so they can do calculation for the electron structure community. I was quite fortunate to be mentored by Dr. Chao Yang at LBL. We still collaborate a lot, and to do exactly that. Another nice thing was I feel I need some dedicated amount of time, so I hope to do that without the pressure of teaching. So IRS fellow was the perfect combination, and I like Berkeley. I did a summer intern here in 2019. At that time, intern was still an in-person thing, right? Nowadays, intern is mostly in the context of remote, but now I came to Berkeley. I like the area. So yeah, so that's how I took the position. I was also feel very fortunate that two ideas that originated from my thesis, one is called PEXI, the other is called Discontinuous Galerkin DFT, got funded the first year I arrived here by two different DOE startup programs, which was relatively rare and really got the time and the resource to develop both of them. And now, for example, PEXI is used in a number of electronic structure softwares called Big DFT, CP2K, DFTB, blah, 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 and can really be used to do like a very large scale, like 10,000 atom or even larger calculations. And this year, the DG PEXI thing just made into the finalist of the Gordon Bell, finalist, like for the SC this November. Then I became a research scientist in late 2013. I found that I still wanted to teach, and I was then hired by the Berkeley Math Department in 2014. I feel again extremely fortunate about this because this is, to my knowledge, perhaps the first hire by a math department in the US for someone with the main focus on electronic structure theory. I mean, really, when I started as a PhD or started as even Alvarez, or pretty much by the beginning when I started to be on the job market, it wasn't clear at all that any one math department want to hire someone like this. I mean, electronic structure, what kind of thing is that? So I was really just to give it a try. I was perfectly happy to stay at LBL, but I was feel quite fortunate. I was hired by the math department and then also joined LBL as a faculty scientist. My PhD and postdoc worked a lot on DFT with functionals at the lower ladders of this Jacob's ladder towards the chemical accuracy. These are so-called the local and semi-local functionals. I became more interested in algorithms for more accurate functionals or post-DFT methods or excited states and those things that are really beyond what the description of a ground state DFT. One example was this adaptively compressed exchange method. For hybrid functional calculations, which is one rank higher than the local and semi-local functionals, but there are a lot, of course, things beyond the Fock exchange algorithm. And this thing has been seems to be a useful development because has been integrated into this pretty widely used packages. And the ACE algorithm is pretty much often the default algorithm solver in the plane wave electron structure community for hybrid functional calculations. So, but there's still a question remains, which is how do you deal with something that is really beyond the realm of DFT, such as strongly correlated quantum systems? I don't have great idea, and the plan was to gradually work towards it. Especially, I spent some time thinking about quantum metabolic perturbation theory and renormalize the diagrams and hope to find answer there. And also tried some time to look into tensor network methods. Of course, nowadays, these are very hot topics, but they do come with their drawbacks. My interest in quantum computation started really around 2017 or 2018. In 2017, I think it was in the summer of 2017, And I was asked by Jonathan Carter, who's now associate director of our lab, and Bert de Jong, who's now like a group lead also our interim division director. Is that right? So is that right, Jackie? So
I have no idea actually.
Anyway, yeah. So at that time he was a group lead of this chemistry thing at the CRD, and the joint proposal for quantum algorithm team organized by the DOE. So I asked myself why I was asked, invited to join this proposal and this, which was funded later at all. My interpretation was that I was perhaps the least square solution at the time to the problem of finding a mathematician working in the quantum sciences at LBL, but maybe a little bit beyond LBL too. Because quantum in 2017 was really quite a niche thing, and very few people in math really work on that. I found it was kind of interesting. Our former Alvarez fellow, Jared McLean, was still at the lab. We talked a lot at the time at the Building 50S, and he introduced me these thoughts about quantum Krylov ideas. Quite some time ago. And eventually we were able to write a paper on quantum Krylov last year. After a few years, I finally understand what that is talking about. But indeed, that brought me to my attention because although it wasn't clear whether quantum computers can be usable one day, it does seem to provide some sort of an ultimate answer, at least at that time, seems to me. And probably still seems to be the case for general audience right now, which is it provides the ultimate answer to solve strongly correlated quantum problems, but also high-dimensional problems in general, with potential infinite limitation, potential infinite amount of power to solve these very, very challenging problems. This is basically Feynman's idea 40 years ago, so-called solve nature by nature. And in 2018, I joined the summer school at the Simons Institute, organized by Professor Umesh Vazirani and other people. I think Andrew Childs was involved there. And I listened to some talks, especially Andreas Gideon announced their quantum singular value transformation. That was pretty eye-opening to me. And I found it was very interesting and started to get hooked to work on the quantum information science as well. But my primary focus is still how to use quantum information science to really try to address these strongly correlated quantum problems. Okay, so that's a pretty long introduction about myself. Now let me talk a bit about this quantum eigenvalue problem, at least the background of it. And as I said, my plan is not to talk about technical detail unless you ask me to do so. The quantum computation meets the public attention really in 2019 and also later in 2020 by this so-called quantum supremacy experiments. So the idea is proposed by John Preskill in 2012. He defined two things. One is quantum supremacy, which is the point where quantum computers can do maybe totally useless thing, right? Regardless of whether the tasks are useful, to do things that classical computers cannot do. And the second question he asked is controlling large-scale quantum systems merely really, really hard or ridiculously hard? Now, with an interesting twist, very in the past few months, I mean, for 2 years or 3 years, people thought quantum supremacy has been firmly established. And then people start to ask a question about asking quantum computer to do something useful, which is called quantum advantage. But in the past few months, there seems to be a growing consensus, or at least a growing viewpoint in the community that quantum supremacy hasn't been reached after all, when you take the inevitable noise level into account. But this is not going to be covered by this talk, but I think it's an extremely interesting development
that has happened within this community. You might have heard that there are a lot of industries establishing their quantum groups. Some are like a dedicated quantum computing companies, Rigetti at Berkeley, or Zapata, or I don't know, Google, PsiQuantum, D-Wave. But there are also other things that you may not really think that they have something to do with quantum, like Amazon or Honeywell, right? I mean, why does Honeywell have anything to do with it? And now, I mean, the quantum program has a spin out of Honeywell, but they did have a quantum group themselves. So there's definitely a lot of industrial, academic, and national lab interest from the national lab to investigate the quantum information sciences together and try to understand the potential in all aspects of doing all aspects of science. So what is a quantum computer mathematically? It is not too complicated, really, conceptually. You have a vector which is very large, called C to the n. Capital N is 2 to the small n, where small n is just a name called number of qubits. It should satisfy some L2 normalization condition. So the biggest assumption of a quantum computer, or the so-called solved nature by nature, is there exists a wide range of unitaries, U, so that U psi to n psi, this matrix vector multiplication can be efficiently performed with very tiny cost compared to classical computers. The cost is polylog with respect to the Hilbert space dimension. This is absolutely unheard of in the classical world because just to read all the vectors requires n cost. And this says in the quantum world, U psi can be performed with polylog n cost. This is really the source of all the possible speedups given by quantum computers, but also the source of all the limitations of quantum computation, because here U has to be a unitary. Obviously, not everything is a unitary operation. Finding the eigenvalue and finding the eigenvector is not a unitary operation. So the question of quantum information science is really to try to see whether you can use like this very powerful tool, but also very restrictive tool to accomplish as many tasks as possible, as efficiently as possible. So any quantum algorithm eventually look like the following. You design carefully a sequence of unitaries. This can be very long, and you apply this to some initial state, and then you read the classical output by measuring one or a few qubits for a number of times. So the cost, or the so-called query cost, in querying the U is roughly speaking the number of measurements times the length or the depth of the circuit times a polylog n, where polylog n is really here. Sorry, this is not the query cost. This is the gate cost after multiplying this polylog n. So one might ask, like this polylog n seems to promise there could be some exponential quantum advantage, or EQA. Indeed, this is at least informally mentioned a lot in the literature. There can be exponential quantum advantage. There can be potential exponential quantum advantage. There's a very promising to deliver exponential advantage, so on and so forth. You see this kind of statements all over nowadays. When would exponential quantum advantage be reached? This would be the case if indeed each of this operation is polylog n, and the number of measurements and the circuit depth should both be polylog n. Then you multiply everything together, it becomes a poly n. You also need to show that classical algorithm, there's no better classical heuristics to go around this problem. They indeed have to work with this large Hilbert space so that the cost is a poly n. Only if you achieve both, you would obtain the so-called exponential quantum advantage. So all of this thing and this and this classical cost,
these are very non-trivial things and needs to be established very, very carefully. So my interest in the past few years, especially after I starting to listen to join the Simons program in 2018, I became very interested in numerical linear algebra and how to use quantum algorithms to handle numerical linear algebra tasks. This really underlies a lot of numerous applications, but for me particularly, in quantum sciences, at the bottom of it, you need to carry out some really large numerical linear algebra operations. This includes a bunch of things that are we all very familiar: ax equals to b, least squares, eigenvalues, so on and so forth. So this kind of tasks, some are easier to be represented by unitary operations, such as e to the iht. Some are less obvious, like A inverse or even precondition, or how to perform a singular value transformation. So how to carry out quantum numerical linear algebra operations, I mean, it's not that obvious, really. I think in the past few years, there have been many interesting and exciting progresses along this line. I think in the next few years, there will be more. So it is a rather exciting era that we're in to develop methods, quantum algorithms for the scientific computing applications. So I started a graduate course last fall, and I see that several people in the audience who were there too, and so I wrote some lecture notes on the quantum algorithms for scientific computation. This is pretty rough notes, but hopefully it will be refined in the next year or so, and to really make it more suitable to a more general audience who are interested in this very fast evolving field. I think quantum linear algebra is one reasonable way towards achieving quantum advantage. At least when you can reliably do quantum linear algebra operations, you can start testing these algorithms and see how do they actually compare with the classical things, not only on paper, but really for actual tasks. For this talk, I really just to focus on one thing, that is the ground state energy problem. So the problem is as follows: you're given H, which is a capital N by N Hermitian matrix called the Hamiltonian, and you want to find the algebraically smallest eigenvalue called lambda 0. This is called the ground state energy, and to prepare psi naught, that is ground state. And what we want to know is under which condition the constant can be polylog n to have some hope of exponential speedup. So to set up the problem in more detail, we're interested in this eigenvalue problem. We need some efficient input model for the Hamiltonian. The Hamiltonian can be local or sparse, something. If you don't have any assumption, this problem is actually very, very hard. This is called like a QMA hard, which means that the task is pretty difficult even for quantum computers. Local Hamiltonian problem without really any additional assumptions. So you do need some physical relevant assumptions. The first one is you need a good initial guess, which is this overlap between the initial state and the ground state needs to be lower bounded by something that's called gamma. This gamma can be small, let's say 0.001, which is okay, but it couldn't be 0. If it's 0, then you're back to this regime. The second one is the spectral gap assumption. That is, the gap needs to be between the first excited state and the ground state needs to be bigger than 0. This one is more important if you want to prepare the ground state, but if you just want to know some ground state energy to precision epsilon, this is actually only optional, because let's say if the first excited state and the ground state energy difference is really small, then you can really just say like the first excited state is also a pretty good approximation to the ground state energy. So is there a quantum advantage for quantum chemistry? I think back in 2017 or so, really the whole thing started also at Berkeley by Alan Aspruch-Guzik, together with Monty Hagorden. That's like 17 or nearly 20 years ago. They used the variational quantum solver to really do some of the basic calculations. About 5 years ago, there was a huge excitement in the community, and a storyline gradually emerged saying, okay, so we need a poster child for this community. What is this poster child? It is called a FIMOCO. And this FIMOCO is a primary cofactor that is related to nitrogen fixation. So the storyline is that we need to spend an enormous amount of energy to just make fertilizer, but or specifically fixing the nitrogen into the compounds. But in nature, the plants can do this extremely efficiently. Why that is the case? And they identified this thing, which is only a dozen atoms, but the ground state structure is still an open problem. It is very intricate, and it seems like the existing classical methods seems too far away to really accurately resolve this problem. And they think that with fault-tolerant quantum computers, maybe we can really one can shed light on the structure of the ground state of this FIMOCO. So that's a good story, but what should you do in practice to actually tackle this scientifically? You need to write down a quantum many-body Hamiltonian written in the second quantized formulation. In general, a quantum chemistry Hamiltonian takes the form of a Hamiltonian as a summation of coefficients times creation and annihilation operator. And this is called the quadratic operator because it's quadratic with respect to C. And this is called the quartic operator that's related to the Coulomb interaction. So you can use this formalism and write down a Hamiltonian for the FIMOCO, but now you can get ready to try to find the ground state. But you have this daunting task of finding this good initial state phi. Remember that without this initial state phi, finding the lambda 0 and the ground state starting from some random state is non-starter for quantum computer. Quantum computer may sound very, very powerful, but if you don't have this initial state, really it is very, very difficult for quantum computers as well. So earlier this year, this is really a work led by Garnier Chan's group, and both you and myself are co-authors of the paper. We question whether there is a strong evidence that we can get exponential quantum advantage in quantum chemistry, particularly for things that are actually simpler than FIMOCO, but you extrapolate towards the FIMOCO regime. The answer is, at least the evidence is very murky. And there's a lot of debate. Whether EQA is the top, that should be a reasonable task for quantum chemistry. And if you find it is a reasonable task, how would you actually verify that? But my personal perspective, at least at this point, is that even EQA would be great, but EQA relies on too many assumptions in most cases. As long as you can show that there is very reasonable polynomial speedups for some interesting problems, I think that is pretty good, because this is indeed seems to be the perspective, even going back to the quantum supremacy experiment. People in the past 3 years have been thinking that, or 2.5 years, thinking quantum supremacy experiments, they are very well established, but and that's definitely exponential separation between quantum and classical. I think the new evidence, theoretical and numerical, starts to suggest that it is even murkier in this very, you can call it a crystal clean problem.
those useless. In this case, one might be expecting just a polynomial speed up as well. So I would say that, I mean, if there's some take-home message, or if you haven't been working on this, the quantum computers can be used to solve eigenvalue problems. They are, but don't set your goal to be exponential quantum advantage from the beginning. And more, at least from my perspective now, having a more polynomial gain here and there seems to be more realistic and could be really transformative when we have a working quantum computer. Let me spend some time. I just realized I don't have a phone. Let me check the time. Okay, so I think I'm doing good on time. So let me talk a little bit about the input model. So the dimension of the Hilbert space is capital N equal to 2 to the n. We'll want to get access to the initial state UI, which prepares this state. Use a unitary to go from a completely trivial state to the initial state. The Hamiltonian, the access to the Hamiltonian requires careful discussion because there are at least two prevailing input models today. One is called block encoding, or BE. The basic idea is H itself is not a Hermitian matrix. You put this Hermitian matrix, which is non-unitary, you put this non-unitary matrix to a corner of a unitary matrices, maybe after some scaling factor. And then for some cases, you use M extra qubits or so-called ancilla qubits. You can achieve this. And then you can use UH to get access to the information in H. The second is the so-called Hamiltonian evolution access, which is UH equals to exponential minus I tau H. You do this unitary evolution, and indirectly you get access to the information in H. You can think like conceptually you're doing a matrix logarithm to get access to matrix H, but you often don't need to perform this matrix logarithm explicitly. We assume that the cost of implementing or the gate complexity of implementing UH and UI, they're polylog n, and what we really worry about is like the query complexity, like the number of accesses to this UH and UI in order to accomplish a given task. So now let's say, what are the textbook algorithms with Hamiltonian evolution access in order to find the ground state? And this is called the Kitaev's algorithm. Kitaev's algorithm is a relatively simple algorithm. Well, if you haven't seen this at all, this looks still pretty rather complicated. But if you have seen something, this is indeed one of the simplest quantum algorithms. What you do is to introduce one ancilla qubit, and you have this Harman gate, and then you have some controlled Hamiltonian evolution Harman gate, and do some measurements. If this is the exact eigenstate with the eigenvalue lambda, and you set this n equal to 1, what you end up measuring, the success probability, you can only get with 0 or 1. The success probability is called P0, and that is the real part of this phase, or cosine lambda. And you do R cosine operation, you will get the information of the lambda. So the cost of this is order epsilon to the -2. This is a typical Monte Carlo type of accuracy. So you need to reach precision epsilon, you need to repeat this for order epsilon to the -2 times in order to get the precision epsilon. The Kitaev's algorithm says that you can trade between the circuit depth, which is how long your operation, your evolution is, and how many times you really measure you do these measurements. So if you allow yourself to use a much longer circuit to depth 1 over epsilon, the total cost will be order epsilon inverse 2. and this reaches the so-called Heisenberg limit. That means you cannot go, you cannot get epsilon to the minus 0.5. No, in general, there doesn't exist such an algorithm. You can also modify this with an inexact eigenstate and with other methods. You can also use the standard textbook quantum phase estimation, which is a very famous algorithm, analyze like a Shor's factorization algorithm and many other things. In this case, you use multiple control qubits to store eigenvalues in the quantum register. You run this thing multiple times and take the lowest value as your estimate to the ground state energy. And this works pretty well either if phi is an exact eigenstate or if it's inexact eigenstate. So you might say, okay, so there are already a number of options in the literature, and why do you stop there? Why don't you just use these algorithms and for the task of finding eigenvalues? You can, but to answer this, we do need to study what are the complexities with this of this algorithm, especially assuming we can query e to the minus IH. We ask what is the query complexity, which means the number of times you need to query of this e to the minus IH with respect to gamma, that is the overlap between the initial state and the final state, epsilon, the precision, and perhaps gap. We also want to know how easy it is to implement. Is that suitable for so-called early fault tolerant devices, especially when the number of qubits is actually very, very small. Another take-home thing I want to deliver in this message is really to get you start thinking about early fault tolerant quantum algorithms. Roughly, the quantum algorithms fall into these three categories. There's the near-term things, which is what we have now. They're really crappy. They're much, much, much crappier than the earliest classical computer in the 50s or 40s, in terms of this error tolerance and so on and so forth. Then there's the early fault tolerant device. We still don't know when it will come to become mature in the full form. But people are making a lot of very exciting progress towards there. And then there's the fully fault tolerant quantum computer, like we're running a laptop, like right now. It is extremely powerful. That one, nobody knows when it's going to happen. So therefore, the near-term things, people generally, at least a large part of the community, have agreed that they have rather limited capability. It is rather hard to expect these near-term devices to outperform classical computers. I mean, for any or most, at least most of the interesting tasks. So that makes the early fault tolerant regime extremely interesting. So it really makes sense to think about how to design quantum algorithms that are suitable for the features of these early fault tolerant devices. There are a number of things that one should keep in mind. These devices most likely are going to have a very limited number of logical qubits. It can be very difficult to execute certain multi-qubit control gate operations. And so particularly difficult are those so-called high-level multi-qubit operations. Those are something like you take a quantum median, or if you want to ask the quantum computer to compute a cosine of a number that's stored in the quantum register. You can do it, but the amount of extra number of qubits, number of gates you need to carry this out is pretty daunting. And it's really, you kind of want to avoid this type of operations at all costs. On the other hand, there are some low-level quantum operations that you might be able to afford. And these are like something like a reflection operator.
and which really requires very small number of ancillary qubits. You know precisely how many there are, and you only need some sort of like ON 2-qubit gates. So these things, I mean, if you can avoid them, that's great. But if you have them, probably that's not the end of the world. It can also be important to prioritize in reducing the circuit depth, because the circuit depth is related to the maximal coherent time of the quantum computer, which is harder to do than running it for many, many times. So even in some cases where you need to do a large number of repetitions, at the expense you have a much shorter circuit depth, this is also can be quite beneficial. So from the lens of the early fault tolerant quantum computer, we can now investigate the different input models and associated algorithms for quantum eigenvalue problem. So I talked about block encoding access. Let's remind you that the block encoding is to put the Hamiltonian in the corner of the unitary. It is easily said than done. You can it has a lot of advantages. It is very natural to express non-unitary matrices in terms of quantum circuits or unitary matrices. You can perform a very large range of tasks of matrix functions, and especially using the so-called quantum singular value transformation. But the drawback is also very daunting. All the interesting block encoding examples today require many ancillary qubits, high-level multi-qubit control, and therefore people generally think these are more suitable for fully fault-tolerant quantum devices, like use the block encoding of a sparse matrix or something. It is very, very challenging to implement. Recently, like with Roel van Buemen, Dan Kamps, and Chao Yang, we wrote a paper detailing the process, such a process. From the beginning to the end. And you can kind of see that they are really difficult to construct. Hamiltonian evolution access, on the other hand, the implementation can be ancilla free. And for example, using the Trotter method, this is perhaps the most important reason for stating that this Hamiltonian evolution access can be suitable for early fault tolerant quantum devices. And this is precisely what was like done when demonstrating some QPE experiments like for tiny quantum chemistry models. Of course, Trotter methods introduces its own discretization error, but traditionally people used to think that the Hamiltonian evolution access, like using QPE, is kind of inferior to the block encoding access in terms of the query complexities, leads to suboptimal complexities. But our recent study and also from other groups as well, really started to reveal that there's perhaps no loss of suboptimal query complexity. It would be too early to say that this is true in general, but there's very good reason to think that if this Hamiltonian evolution access is used correctly, that is probably a more promising way towards achieving quantum linear algebra in the relatively near future. Okay, so my last two slides of the talk is really a summary of the progress of for ground state energy estimation and for ground state preparation, respectively. There's a tons of information. It can be hard to decipher if you're not already working on that, but I hope give you some basic idea in terms of what people and also from our group are really focusing on in terms of this kind of tasks. The task is you're already given an input model, Hamiltonian evolution block encoding, and you assume you're given a good initial state. The only question left is how many queries to the Hamiltonian is really needed in order to find the ground state energy to precision epsilon. So we care about the scaling with respect to epsilon and with respect to gamma. You can see that why we don't stop the QPE. So the QPE with the high confidence version, the query depth or the circuit depth or like indicator of the circuit depth is very good. It's epsilon inverse. the query complexity is epsilon inverse gamma to the minus 2, which isn't bad, but the number of ancilla that is used, and also the need of a multi-qubit control is inevitable. So this is not likely to be implementable in the near future. For things that is implementable in the near future, the cost with respect to the gamma is extremely unpleasant. So it's gamma to the minus 2 and gamma to the minus 4, respectively. So if gamma equals 0.0001, and you're pretty much screwed. There have been other improvements by Rolando Soma's group. You get this kind of query complexity, or Cirac's group with this kind of depth and complexity, together with a high level of multi-qubit control. So none of them is really satisfactory. So the first thing that we made in early 2020 with Yutong and was to achieve the nearby optimal complexity, epsilon inverse gamma to the minus 1. You can find that there's no such complexity before. Using the block encoding input model. Still, I mean, it's nice to demonstrate this works, but we don't expect that this can be implemented in the near future at all. And then there was another progress together with Yutong, leads to a much shorter circuit depth, and that is implementable on early fault tolerant quantum computer. But the query complexity is kind of like here. It's still better than this algorithm, but you have this gamma to the minus 4, which is undesirable. Finally, earlier this year, with Yulong and Yu, we proposed two algorithms that, on one hand, it achieves, it matches the very short circuit depth of the early fault tolerant algorithms, and pretty much get this gamma to the minus 2 for free. And the key is we developed something called quantum eigenvalue transformation for unitary matrices that really bridges the gap between the Hamiltonian evolution based methods and this QFET based methods, and it shows that there's no fundamental gap between them after all. And you can further borrow ideas from this near optimal algorithms and achieve the near optimal complexity using Hamiltonian evolution input model, and that is really suitable for early fault tolerant quantum devices. So this is a lot of information, but I want to say for ground state preparation, the story is very similar. The main difference is you should replace the epsilon by delta in most of the places, and there are fewer algorithms that are applicable, such as this algorithm and this algorithm. It cannot be used to prepare ground state without significant modification. So the table is shorter, but again, with this new developments that we're really quite excited about, you can get near optimal complexity that is suitable for early fault tolerant devices. I think my time should be up. Oh, exactly up. So
nice
I will
timing.
just So this is really, as I said, the end of the talk is the end of introduction. But if you have questions, please feel free to let me know.
I have an sorry, I have a question. But I'd like to give the audience a chance to ask their questions first, because we are almost out of time. Does anyone have any questions from the audience?
Hi, I have a question. Hi, Lin.
Yeah.
So I don't know anything about quantum computing, but there is one problem I'm very confused. It's because, as I understand it, what you just presented basically is to design quantum algorithms which potentially can be run in quantum computers.
Right.
So when you really, test, whether this kind of algorithm shows advantages using quantum computer for some computational tasks, how do you really test it? Do you really test it in quantum computers, or any kind of numerics? How is it really be done? I'm a little bit confused.
Yeah, so the verification is a very big topic. Probably deserves an independent interest. So there are ways to show that, quantum computer is really doing the quantum stuff. and Professor Umesh Vazirani and many other people, especially in the computer science program and at Berkeley, they're very dedicated to that. What we assume here, or from my perspective, the task of the quantum algorithm field is pretty much to assume the quantum computer is working, one, in the sense that it is error tolerant, error fault tolerant. Two, it is doing it faithfully, which is it's not some just a black like a box. You give it some number, some other people run this calculation on the classical computer and feed you back the answer, right? So assume this kind of verification tasks have been done. Then the central question is really to say that how many times do you need to query certain oracles? It pretty much boils down to this question. Does that answer?
Yeah, kind of.
Yeah. So I want to really separate these two. So what you ask isn't really isn't really the job of the quantum algorithm community. It's for a separate community.
Okay, I see. Thank you so much.
Yeah.
Any other questions? Okay, I will ask my last question. Could you comment on the energy consumption of the potential quantum computer? Because we know that for classical computer, right, the energy consumption is really becoming a concern, and we're expecting that within 20 years, the cost for each calculation will be many times more expensive than now. Is this a concern for quantum computer, or is it too early to worry about it?
I think it's probably too early.
Okay.
Because the energy. Actually, interestingly, So I kind of personally witnessed this energy questions being asked. I mean, at the beginning, not many people ask these questions, right? In the past 10 years. See horses there. Horses care about lots of these things, and really in the past 10 or 15 years, people ask this more and more. And this is to me, someone like me, this is because it becomes increasingly clear what are the different balancing factors that are really worry us in terms of supercomputers. For quantum computers, we're really far from that, because we need to achieve fault tolerance, and there are numerous. There are a number of proposals for fault tolerance. It's very hard to evaluate the pros and cons without actually doing them and doing them at a scale. It's not clear any of them is scalable, right?
Yeah.
So at this point, I would still think that the idea of a quantum computer is you use a lot of resource. Hopefully, you don't need a nuclear plant to power it, but you use a lot of resource to achieve something first. I think we're really at that stage. We're so far away from thinking about, energy consumption is our limitation, and we're just limited by so many other things.
Got it. Yeah. So it's more like scientific research for now. We don't look at the real estate.
But because even for classical computer, the energy consumption thing, has become a mainstream question only in the past, 10, 15 years or so, right?
That's because Moore's law is coming to the end.
Yeah, that's right. Yeah. So, and for quantum, we're really at the pre-Moore's law stage.
Okay.
Right. So it's really hard to talk about the time span and so many years.
Yeah, making sense. Great. Okay, so this is our seminar session for today. Thank you everyone for attending. We will have our next seminar in 2 weeks. So that's it. Thank you so much for your time.
Yeah, thanks, Jeff.